Yeah, before we start, I would like to mention that this module of MS1 you can use irrespective of which software you have used for data analysis. So even if you have used some other software for pre-processing of the data, you can download the data and you can prepare it in a particular format, upload the CSV on MetaStat and perform the processing. So for that, let's click on MetaStat. I'll click on parameters. Now the first page that appears will ask you to fill some parameters. So this is just about, so the data that you get might be sometimes bad, will have junk or variability. So before you perform the processing, you need to prepare the data for the machine learning algorithm to work on. So these are the few parameters where you remove the variability and so on. So first is filtering the data. So how much percentage of missing values are allowed in the data. So there can be some missing values because the value was not present in the sample at all, or the instrument could not acquire at that particular time. So yeah, you need to fill some percentage. Then you can filter the data based on the CV. So metabolites having higher variability will be excluded from the analysis. Then there's an option of features where you can choose if you want to do it with just annotated features or you want to perform the statistics on all the features. Then to perform machine learning algorithm, you can't leave the values empty. So since we have allowed 20%, for example, the missing values, you need to impute those values with some value. So when you click on this, you get multiple options to impute the values. Now, choosing which option totally depends on what study you are performing or what's your interest. For example, if you're working on a biomarker related study, you can go ahead with KNN sample group wise, where it looks at the nearby samples and imputes the values accordingly. Or for example, if you have data from time course experiments from a fermenter or so, you can maybe go ahead with LOD or LOD feature or LOD global. And so on. There are multiple options you can choose based on the study that you're working on. Then there is an option of blank subtraction. So whenever you have a data, it might be possible that few metabolites that you are seeing is not the true feature present in your sample. It might be coming from the blank that you have run. So you need to definitely remove those metabolites. So that's where this helps. You can put a cutoff over here. So whatever metabolites you see in the sample, which are more than, for example, threefold compared to the blank, will only be considered for the analysis and rest other metabolites will be removed. Then comes the normalization. Now the data is never acquired in one batch. You acquire data in multiple batches. So if you want to compare data which is acquired today and the data which was acquired months back, you need to have some normalization technique, as these instruments are quite finicky and they vary in their intensities. So these are the options available over here to normalize the data. If you're working on cohort kind of studies, you can use median normalization. Or if you have something where your data is time point dependent, this might not work. So you need to go ahead with QC normalization. So in general, we always recommend you to inject as many QCs as possible. So that's the best way to normalize any kind of data and works well for most of the data. So yeah, these are the multiple options to normalize the data. And then most of the data that you acquire are sometimes they are skewed and might not work when you perform machine learning algorithm on that. So to transform it into normal distribution, you need to transform the data by different methods. You can choose any of them, either log transformation, cube root transformation, or square root transformation. Then the data that you have might have few metabolites which ranges from 10 to the power 2 to 10 to the power 6. So they vary in a scale, huge scale. Now to compare them, you need to bring them to a one common scale because the one at higher end might mask the one at the lower end. So there are different ways to scale your data before you perform any kind of analysis. So yeah, you can choose any of them. For now, I'll just go ahead with the default option and I'll click on process data. So yeah, these are just the way of cleaning the data before you can perform the analysis. And once the data is processed, you can start visualizing. So whenever we get a data, we recommend you stare at your data. And the best way to do that is plot a heat map out of it, because it helps you visualize multiple metabolites at a time across different groups. Now, let's just plot a heat map. I'll show you. These are the options. And there are 4 features. This is too less number to plot a heat map. Maybe I'll just would like to plot top 40 features into a heat map. Now, there's one interesting thing over here. If you have already performed statistical analysis and you know the top significant features, you can create a CSV file with the IDs of those significant metabolites and upload it here directly. So this will help you generate heat map of only those metabolites. For now, we'll just go ahead with top 40 features and I'll click on generate plot. So yeah, here on the right side, you can see a beautiful heat map, which clearly shows you how the metabolites are varying. So on the left side, the red class, which belongs to the healthy, and the green one belongs to the Guillain-Barré. So you can see the top metabolites are upregulated in the healthy compared to the Guillain-Barré, and the bottom metabolites are upregulated in case of the Guillain-Barré, the diseased group, compared to the healthy one. And this is the best way to visualize how the metabolites are changing in forms of just how the color gradient changes. So you have a color scale, red shows the higher intensity and the blue shows the lower intensity of the metabolites. Now, for example, if you want to customize these plots, so that option is also available over here. So these images are quite publication friendly. You can directly download them and use them. Since the study is on MetaMind, you don't see the download option available over here. But in your own study, when you upload it, you will get the download option over here. Now you can also customize these plots. For example, if I want to change the color of the heat map, maybe I would like to plot it in a red-green color. I'll just click on that. So yeah, this allows me to change the color of the heat map. So there were multiple options available over here. You can also change the height of the plot. For example, I want a taller plot. I'll just click on that, and maybe this will give me a taller heat map. So you can visualize each metabolite very clearly. So yeah, all these customization options are available over here, and you can then download your plot after that. Now, if I'm interested in looking at the correlation between the metabolites, I can also click on the correlation. So I'll just click on generate plot over here. So yeah, this helps us visualize how metabolites are correlated, and I'll maybe would like to cluster them together. So I'll click on column cluster. So both row and columns are clustered here. So yeah, here you can clearly visualize this group is correlated. So all these metabolites are highly correlated. These two groups, these metabolites are highly correlated. And there are few metabolites, for example, these dipeptides are correlated with these amino acids over here. So yeah, this is another way of visualizing how your metabolites are correlated or not correlated with each other. Similar to heat map, here also customization is possible. Now this was about visualizing the multiple metabolite at once. Now if you're interested in visualizing single metabolite and how they are changing across the groups, there are multiple options like bar, box, and violin plot. So once you click on it, you can see the table. So here are the list of metabolites. For example, if I want to see how the ornithine is changing, it has been the metabolite of discussion since the beginning of the session. It changes in the Guillain-Barré group compared to the healthy significantly. So yeah, this way you can see how it is changing across the group. Now, what bar plot does is that it plots a mean. Now, if I want to see how the samples are distributed across these two groups, maybe I can go ahead with box plot, and it helps you visualize. You can see the sample distribution and the outliers as well. And same thing happens with the violin plot as well. Now, similarly, lysine can be seen. So there are multiple metabolites, and one by one, you can visualize them and you can download them for your data analysis. Now then there are options of cloud plot and this volcano plot. So I'll show you one of them. What a cloud plot gives is that it works on p-value and fold change cutoff. So it helps you visualize the significant metabolites if they are upregulated or downregulated in just one plot. So what I'll do, I'll go ahead with default options over here. You can definitely change these values based on your, if you want highly significant features, you can reduce the p-value cutoff, or you can increase the fold change cutoff over here. Now I'll just put the first group over here, or the second group, healthy group, and I'll click on generate plot to see the cloud plot. So yeah, now you can see how beautifully this represent all the metabolites which are, so above the x-axis you can see all the upregulated metabolites in the green dots, and the red dots below the x-axis shows the downregulated metabolites. And the beauty of this plot is that you can visualize how the metabolites are changing across the retention time. So there are total 185 upregulated and 117 downregulated metabolites over here. Similarly, you have option of volcano plot. Apart from this, this is just about plot. You can also visualize the data in a tabular format over here. So the same data, you get it in a tabular format. You have metabolites, their M by Z, retention time, and p-value. You can also sort this table. And one very interesting thing over here is that whenever you are analyzing the data for statistical test or something like that, always it's recommended to do some sanity check parallelly. So if I click over here, you can parallelly look at the XICs of that particular metabolite, their MS2 match, bar plot, and box and whiskers plot. So you don't need to go back to Met Analyzer is what I meant. You can parallelly do the statistical test along with the sanity check. This saves a lot of time. Otherwise, in most of the softwares, what you have to do is that you have to go back to the processing software and then see if the peak quality was good, or if you can consider that as a significant metabolite or not. That thing can be done over here parallelly while you're performing the statistical test. So yeah, this was about visualizing the data. Now, performing the statistical test, on the left side, I'll click on statistical analysis. You can, now if a study has two groups, if you want to compare two groups in your study, you can go ahead with t-test. Otherwise, there are multiple options like ANOVA, where you can also compare multiple groups in your study. But if just comparing two groups and find out the significant features, you can go ahead with t-test, which gives you the list of significant features. And fold change analysis allows you to see what all metabolites are upregulated or if they are downregulated. So yeah, I'll just show you what all features are significant. I'll go ahead with the default option. Then you can select the two groups over here, click on generate plot. And yeah, see, this shows there are 405 significant features in the study in the Guillain-Barré group compared to the healthy, and 255 were insignificant. So you can definitely change these values if you want to see only at a highly significant. For example, if I go for 0.01 and generate. So yeah, now the significant metabolites, the number has reduced. Same thing, you can also visualize in the form of table. So all these options you will get in each and every step of MetaStat. So here also, by clicking at each and every metabolite, you can parallelly visualize the MS2 plot or XIC plot and so on. So yeah, then the next option is feature selection. When we talk about biomarker-based studies, so that's where this helps a lot. When we perform statistical tests, typically we saw that we got 200 or 300 significant metabolites. But can they be considered as biomarker panel? No, that typically contains 8 to 10 key metabolites which are responsible for creating the difference. So that's where this feature selection helps. So we have multiple algorithms present over here: ANOVA, mutual information, recursive feature elimination, random forest, and so on. So I'll show you one of the algorithms to find out the key features. I'll click on submit. So this gives you a table which is sorted in ascending order of the p value and descending order of the f value. And if I click on this gamma, glutamine, lysine, any of the metabolites, you can parallelly see. So these are the top few metabolites which are most significant and can be considered as a biomarker or the key metabolites. So here also parallelly you can visualize. So here you can see that how these two are very close peaks, but still the peak boundaries are so well defined if you see over here. So you can see the unaligned XIC, aligned XIC, and you can also look at the MS2 match. So you can zoom in, zoom out. All these options are available over here. Now, there are other algorithms as well. You can feel free to explore them. Apart from this was all about visualizing one metabolite at a time or performing the statistical test on that. Now, if you want to see multiple metabolites or just want to see the difference across the groups altogether, there are options like unsupervised learning and supervised learning, which helps in dimensionality detection basically. So I'll go through the unsupervised learning where PCA comes into the picture. So here when I click on the generate plot, it shows a nice PCA overview where you can see that PCA1 is 27% and PC2 is 7.5%. So this shows that PC1 is sufficient or two components are sufficient to explain the difference between the two groups. Now I can go ahead with two components and plot the PCA plot. And yeah, this helps you visualize the difference between the two groups along with the outliers. So these are basically the outliers. And you can see there's a difference, there's actual difference in between the healthy as well as the Guillain-Barré group over here. Similar to PCA, supervised learning also works on the same line. It's just that it looks into the classes given to the samples. Now, PLS-DA is a kind of supervised learning. It also calculates a VIP plot. So I'll quickly show you how the VIP plot works. It calculates a VIP score. I've given top 10 features. I can maybe go ahead with 15 and I can look into the VIP score of top 15 metabolites which are responsible. So yeah, it gives you a plot, and so on the y-axis you get the metabolites, 15 top metabolites and their VIP score. So these are the metabolites which are responsible for the difference that you see across the two different groups when we were plotting PCA plot or PLS-DA plot. So yeah, this was all about unsupervised, supervised learning, performing statistical analysis, and visualizing the data in different formats. Feel free to use MetaStat for your own data if you have. And if you don't have your own data, maybe you can try it on the studies which are already available on MetaMind.